So welcome to this class. In this session, we are going to prove the Taylor series or Taylor theorem for function of two variables x and y. So the statement reads, if f of x, y is a function of two variables x and y, and its partial derivatives up to the nth order are finite and continuous, for all points x, y, where x is between a and a plus h, and y is between b and b plus k, where this h is simply the change from the point x to the point a, and then this k is also change of y from the point b. Then the value of the function at a plus h, b plus k, is given by the value of the function at the point ab plus summation m from 1 to n, 1 over m factorial into h partial x plus k partial y raised to power m, f at ab plus 1 over m plus 1 factorial, h partial x plus k partial y raised to power m plus 1, f at a plus theta h, b plus theta k. Remember, theta is a number taken in the interval 0 to 1. So let's prove this theorem. So can highlight this. So this is a statement that we need to prove. So proof. So this statement can be written as f a plus h, comma b plus k equals to f at ab. Now I want to write a few terms in this summation. So when m is 1, then 1 over 1 factorial, just 1. So I have h partial x plus k partial y, and then the value of the function at a, b, plus when m is 2, we'll have 1 over 2 factorial into h partial x plus k partial y raised to power 2, value of the function at ab, plus next when m is 3, we'll have 1 over 3 factorial into h partial x plus k partial y raised to power 3 f at a, b, and then plus other terms in that pattern. So this is what we need to prove. So to prove this, the assumption is that you know the statement for Taylor series for function of a single variable, fx at a point x equals to a. So recall that the Taylor's theorem for function f of x about a point x equals to a is of the form, or is given by f of x equals to f at a plus x minus a, first derivative of the function at a plus x minus a raised power 2 over 2 factorial, second derivative of the function at a plus x minus a power 3 over 3 factorial, third derivative of the function at a plus other terms. And when we fix x minus a to be h, then we have f of x is equals to f at a plus, so this would be h, f prime at a plus this would be h squared over 2 factorial, second derivative of the function at a plus this will be h power 3 over 3 factorial, third derivative of the function at a plus other several terms. So let's call this one 1. This Taylor's series or Taylor's function of a single variable f of x. So we assume that, let's suppose that now for our case, f of x plus h, comma y plus k is a function depending only on one variable, say x, so that y is assumed to be constant. So we have a function f of x plus h, comma y plus k. So we're assuming that this function is only depending on one variable, say x, and so we take y to be a constant. So that's the assumption that we give. So then we expand f of x plus h, comma y plus k by Taylor's theorem for function of a single variable. So in this case, because we are saying that we are taking the variable to be x, so y is assumed to be constant. i.e., so we'll have the function f of x plus h, y plus k is equals to, so remember, so because we are saying that y is assumed to be constant, so we are going to write the same, this same formula for this one, but the only change is that where there's derivatives, we now have partial derivatives because we have x and y, and the place where we have this part of y remains the way it is, y plus k, but then we use the same structure in this Taylor's series of the first function of a single variable. So the first term will be f at x, comma y plus So I hope, because from what we said here, remember you can write as well, because x minus, just to see clearly what's happening. Also saying that x minus a is h, so which means that where there's x here, we can write it as x equals to a plus h. So that formula is f of a plus h is given by this. So therefore, the next, so a plus h, so it's like our a is x in this case. So we have x plus h. So therefore, we'll have, where there's a, we put x, and then actually if you x plus h, then a plus h. So in this one, using this structure, the place of a is taken by x. So therefore, the first term will be f x comma. This one is not changing, so it will be y plus k plus, next one is h, and then because now this is the first derivative, so there'll be partial derivative of the function with respect to x, and then the value of the function at, this is x. This one, remember, is a constant, so that's not changing. So we have y plus k plus h squared over 2 factorial, and then partial squared, partial x squared, and then the function is still x comma y plus k, and then plus, next is h power 3 over 3 factorial, third derivative of, with respect to x, the function remains to be x, and then y plus k, and then plus other several terms. So remember, what we're doing is just checking this structure of the Taylor series of a function of a single variable. And because our case, we are dealing with f of x plus h, and then y plus k, and we are assuming that y is a constant, so we are not interfering with this part. So this is the only part we are dealing with. So we're just using the same structure, and when you relate this one, a plus h, x plus h, so the role of a in this equation will be taken by x, and then this one remains fixed. So that's why we have this equation here. Let's call this one 2. So next, we also apply Taylor's theorem for function of a single variable to this now function f of x comma y plus k. We just repeat the same procedure that gave us this 2. Now, for this case, remember this single variable, in this case, this first one was, we are having x in mind. So next year, we are having y in mind to write this one as a series. So i.e., we'll have f of x comma y plus k will be given by, so we'll have now the role of a in this equation 1 will be taken by y, and then the x is not changing. So here the role of a will be taken by y, and then h will be taken by k. So that this will give us f of x comma y plus now k partial y of now f of x comma y plus k squared over 2 factorial partial squared partial y squared f at x comma y plus k power 3 over 3 factorial partial cubed partial y cubed f at x comma y, and then plus other several terms of the same pattern. So here we call this equation, call this one 3. So what we do now, we replace 3 in 2 so that this place of f of x comma y plus k is taken by this series. So using 3 in 2, or simply replacing expression for f of x comma y plus k in 2, we have, so we are going to write the same thing, but where there's this function to replace by this series. So the answer will be f of x plus h comma y plus k will be given by, so the first function here will be given by this series we have given in 3. So it will be f of x comma y plus k partial y f of x comma y plus k squared over 2 factorial partial cubed partial squared partial y squared f x comma y plus k power 3 over 3 factorial partial cubed partial y cubed f at x comma y plus other terms. Then I close that bracket. Our next term in 2 is k, then partial is h partial x of the same function. So we'll have h partial x of now f x comma y plus k partial y f of x comma y plus k squared over 2 factorial partial squared partial y squared f of x comma y plus k power 3 over 3 factorial partial cubed partial y cubed f at x comma y, and then plus other several terms. So that is rewriting the second term of equation 2. Now third term is h squared over 2 factorial. So be plus h squared over 2 factorial partial squared partial x squared into the same f of x comma y plus k partial y f of x comma y plus k squared over 2 factorial partial squared partial y squared f of x comma y plus k cubed over 3 factorial partial cubed partial y cubed of f x comma y plus other terms, then close the bracket, plus next term in 2 is now h cubed over 3 factorial partial cubed over partial x cubed of this function. So we'll have h cubed over 3 factorial partial cubed partial x cubed into the same series f of x comma y plus k partial y f of x comma y plus k squared over 2 factorial partial squared partial y squared f x comma y plus k cubed over 3 factorial partial cubed partial y cubed f of x comma y plus other terms. Then I close the bracket and then plus this next terms. So let's call this one 4. Let's call this one 4. Now we want to simplify 4 so that we bring those terms without partial derivatives together, those terms with one partial derivative together, and those terms with second order partial derivatives together, those terms with third partial derivatives in order, etc. I then say on simplifying 4, we can rearrange terms in 4 to obtain. So left hand side is f of x plus h comma y plus k equals, so we start by those terms without any partial derivative, and as we see, it will be only this term. This is the only term that will not have a partial derivative. So the first term will be f of x comma y plus. Let's pick those ones without with only one partial derivative, and you see it will be this term, and then this term, because this will be now k partial y f x y, and then this is h partial x f of x y. So when you open the bracket, this times this one here. So there's only those two terms. So I can write h partial x f of x y plus k partial y f of x comma y. So I put this one in brackets. So these are the only terms without with only one partial derivative. So let me go to those ones which have which have second order partial derivatives. So for those with second order partial derivatives, I'll have this term, and then I'll have, so remember this is, you have to get the answer for this, you have to have h partial x, then you multiply by what is inside here. So when you take this one and this other one, it will give you second partial derivative but mixed for x and y. And then this term, when you apply h squared over 2 factorial partial squared partial x squared to this one, we also get the next term with partial derivatives of second order. And those are the only terms. These others will have higher order terms. So I'll start by rewriting this one in x. And because this one is at 2 factorial here, so I can factor out 1 over 2 factorial. And then I write partial squared partial x squared f of x y plus, now this other one, this one will have now h times k, so I'll have hk, and then partial squared because this and this one, and then partial x partial y, and then I have f of xy. So this is what I'll have this one here. But you see, I'm factoring out 1 over 2 factorial. So for me, because I'm using bracket, then I need to put here 2, so that when I multiply by 1 over 2 factorial, I still get back my original hk second partial derivative of x and y. So therefore, I'll have to put here 2, and then hk partial squared partial x partial y of the function f of x y, and then plus last one was this one here. This just, because I factored out 1 over 2 factorial, then I just have k squared, then this one here. So I'll have k squared, partial squared, partial y squared of the function f of xy. So those are the terms with second order partial derivatives. Now let me go to those with third order partial derivatives. So I'll have, the first one is this one. And then next one, when I come this one, this second one, it will also give me third order partial derivative. And then when I pick this one with the first one here, because these are 2, then this one 1, give me 3. So this will be also another term. And then I'll have this applied to this function here. I'll get third order derivative. And then this I can see a 1 over 3 factorial here. Also on this other one was 1 over 3 factorial. So what I can do, I can factor it out. I have 1 over 3 factorial. And then I start with the x1, so I'll have partial power 3, partial x power 3, f of x comma y plus. Then you see here, this was second partial with x and then partial with y. So I'll have h squared. I remember this is this time, this one will give me h squared k over 2 factorial, just the same as 2. So I have h squared k over 2. But now I'm putting outside 1 over 3 factorial. 3 factorial is 6. So it's like I have 1 over 6 outside. So that I still have a half for this coefficient. Then I'll have to multiply this one by 3. So that 3 times 1 over 6 give me a half. So therefore the coefficient for this one, because I've introduced a bracket, will be now 3 h squared k, and then this mixed partial derivative. Have 3 h squared k, and then partial cubed, partial x squared, partial y, f of xy plus next one. So I've dealt with this and this one also. This one here are the same thing. So this is h times k squared over 2 factorial just as same as 2. And I have factored out 1 over 3 factorial, which is the same as 1 over 6. So I also need to multiply it by 3 so that when I open the bracket, I still get 2 in the denominator. So I'll have 3 h k squared, and then partial cubed, partial x, now partial y squared of the function f of xy plus, now lastly, so I've dealt with this part, this is just this one here, k cubed, partial cubed, partial y cubed, and then the function at x, y, and then plus other several terms. Let me call this one question 5. Now 5 can be written as 5 may be written as so write f x plus h comma y plus k. So the first term will just be f of x comma y. Second term, because the f of xy is common to this and this one, I have put it out. So I have into bracket h partial x plus k partial y, and then f of x y. And then this one here, what is happening is that to explain what's happening for this second order partial derivatives. So partial x. This one are just taken to be like one number. So when I have in this first term, so remember there was a h squared here. You can see it clearly from where we are getting those. We had this term here, h squared, k squared, and then second one, and then so that h squared was so at this point here. So when you multiply h squared over 2 factorial times this one, this you hit that h squared. That's why I'm putting it there. So these are taken like one quantity, and then k partial y is also taken as one quantity. So if you remember binomial, a plus b squared is the same as a squared plus 2ab plus b squared. And this is what the same thing that we have here. So the coefficient of this one is 1, coefficient of this one is 2, then this is 1. So this one is the same as they took h partial x, and then you square. So that's why I have h squared partial x squared. And then here it's like we have h partial x, you multiply by k partial y. So that's why you have hk, and then partial squared partial x partial y. And then in this binomial expansion, that's why you have this coefficient 2. And then this one is the same thing as taking k partial y, then you square. So you have k squared partial y squared. And then we pull out f of xy, f of xy, f of xy. So it turns out that this would be simply the square of h partial x plus k partial y, this second one here. So we write it as plus 1 over 2 factorial into h partial x plus k partial y, and then squared, and then you pull out f of x comma y. Plus, also, if you remember your binomial work, if you work out a plus b cubed, you get a power 3 plus 3 a squared b plus 3 ab squared, and then plus b power 3. And a is h partial x, b is k partial y. And you can see that these are really coefficients. So remember there was a h cubed here. Just see from here. There's h cubed here. So this is what you multiply to get that term. So h cubed over 3 factorial f of xy. So that's why I'm putting there. So clearly this h cubed partial x cubed is the same as h partial x, and then you raise to power 3. So this one here is just the expansion of this same bracket, but then raised power 3, just as we see in this binomial expansion. So we'll have 1 over 3 factorial into h partial x plus k partial y, and then raised power 3, and then we are pulling out that f of xy. So there's a plus here, f of x comma y. So next sum actually we can predict it will be given by 1 over 4 factorial into h partial x plus k partial y power 4, then f of x, comma y, and then other terms will follow in that pattern. So call this one equation 6. So when you replacing x for A and y for B, then we have the result that 6 becomes, so where we have x, we put A, y, B. So we have A plus h, comma B plus k equals to f of A, comma B plus h partial x plus k partial y, and then f of A, comma B plus, next we have 1 over 2 factorial into h partial x plus k partial y power 2 f at A, comma B plus 1 over 3 factorial into h partial x plus k partial y, and then power 3 f at AB, and then plus other several terms. And actually this is the thing that we were supposed to prove. So this was the statement that we were to prove. So that's the end of the proof. And you can get some special cases for this formula when you replace A for 0 and then B for 0, you can get another expression. So just special cases. When you replace A for 0 and B for 0, remember the proof ends at this point, then it means that because x minus A is h and y minus B is k, then it means that we have x equals to h and y equals to k. So that the formula becomes f of x, comma y. Because remember, this will be 0, this will be h is the same as x, this will be 0, this will be k, which is the same as y. Is equals to f A is 0, B is 0, plus h is the same as x, partial x, plus k is y, partial y, and then f at 0, 0, plus 1 over 2 factorial into x, partial x, plus y, partial y, power 2, f at 0, 0, and then plus other several terms. So that is how we prove that one. So this special case can help us to solve problems when we are finding the Taylor's expansion of a function at the point 0, 0. So thank you.